In this lecture, we shall learn that how we can calculate the aerodynamic shape factor for the solar panels mounted on the ground. So when we're talking about the solar panels mounted on the ground, this is basically one of the picture where we can see the practical example of how exactly the solar panels are basically mounted on the ground. So when we're talking about these kind of solar, we can say panel, we do denote it as array because there are these arrays of the solar panels that are mounted. So, if we want to, as a structural engineer, we are entitled to calculate the wind force on all of these solar panels, and to calculate the, to help us to calculate the wind loads on these solar panels. ES 1170 gives us guidelines in the form of, we can say, figure B.11, and figure B.11 basically help us to calculate the, we can say, the net pressure coefficient, which is then multiplied with the area averaging factor and a local net pressure factor to help us calculate the aerodynamic shape factor. So these are the values of the CPN, that is net pressure coefficient, which when multiplied with Ka and Kl help us calculate the Cshp. Now there is this one more factor, that is Kp, that is porosity factor, which is by default taken as 1 for this particular solar panel case. Now if we want to study about the basics or the applicability, that whether the solar panels are that you are using in your project are applicable as per these particular values or not. So for that we can just simply calculate or we find out the dimensions that are given in this particular figure also. So let us suppose this is basically the ground here. So if we are talking about the first of all the inclination, so inclination is basically alpha. So this is the angle alpha, and this inclination basically help us to calculate the wind load. After that, if we are talking about, this is also known as the pitch, and this pitch has to be less than or equal to 30 degree. If pitch is greater than 30 degree, then this table is not applicable, because the maximum wind load that is given for the 30 degree only. After that, the second, when the panel is attached to a ground mounted frame, so the other parameters here are B, that is this dimension here from this point to this point, that is B, and this is D, and the average height from this point to this point, the average height is H, and the clearance below the ground from where the wind can pass, that is denoted as C. So, and the spacing from one solar panel to another solar panel, this is denoted as S. So when we're talking about the the applicability, we have already studied one first applicability, that is alpha has to be less than or equal to 30 degree. After that, the second applicability is that the C, that is the underside of the, we can say, panel and the ground surface, so C by H value, that has to be greater than or equal to 0.2. After that, third applicability is that basically the spacing, the S, and the ratio of the, we can say, spacing divided with the height. So the ratio of the spacing with the height, that has to be less than or equal to, we can say, S by H needs to be in between the values of 3.5 and 10. And if we are talking about the fourth applicability is that D by H value, D is basically this parameter, and H is basically the height, average height. So D by H basically needs to be in between 2 and 5. So this value needs to be between 2 and 5. And fifth parameter here is that B by D ratio, that has to be greater than or equal to 2. That is, B is basically this parameter and D is basically this parameter. So that has to be, we can say, greater than or equal to 2. So all these are the 5 parameters that needs to be ensured, and after that only we can say that this these net pressure coefficient are applicable on the project that we are working on. And I must say that it is not like that this is an input for you, all of these parameters, and to set all of these parameters you have to sit with the we can say electrical engineer who is designing the solar panels also, or solar panel farm also, and on the basis of that you can just simply sit with them and just say that these are the parameters that needs to be satisfied before we can calculate the solar the wind energy on the solar panels. So sorry, the wind forces on the solar panels. So after that, if we're talking about the practical example, let us suppose in our case the pitch here. So pitch is basically, let us suppose 20 degree, because that is the only we can say condition that needs to be fulfilled. All the other parameters are not we can say function. Only function is the pitch. On the basis of pitch and on the basis of these five ratios or five conditions applicability, we can just simply find out the net pressure coefficient. Now if we are talking about the, we can say, wind force cases, first wind force case is that theta is equal to 0, that is wind is striking directly at 90-degree angle to the solar panel. Second case is that wind is striking perpendicular to it, that is theta is equal to 180 degree. Sorry, wind is striking from the back, that is theta is equal to 180 degree. So that is the basic difference. It is not like that we do not consider the theta is equal to 90 degree or theta is equal to 270 case here, because theta is equal to 0 and theta is equal to 180 are the cases that do govern the design. And that is a basic wind engineering judgment also, that let us suppose this is the solar panel. I just want to share two basic engineering we can say wind engineering judgments. First case is that let us suppose you have these two solar panels. First solar panel is at inclination of alpha is equal to 10 degree from the ground. Second solar panel is at basically alpha equal to 30 degree from the ground. In which case wind force shall be higher? Obviously in this case, because it is providing the maximum resistance, and usually it is fixed at alpha equal to 30 degree only. Why? Because the more the sun rays shall strike, the more efficient shall be the solar panels that are basically installed. So in most of the cases it is usually installed at 30 degree angle only. Second case, the practical example that I want to discuss with you is basically the wind striking angle. In first case, let us suppose this is a solar panel. Wind is striking in this particular direction, that is theta is equal to 0 degree. So in this case, when wind shall basically strike, it shall simply find its way across the top and then just simply blow away. That is the case. Some shall strike and rest of the some percentage shall flow from the ground also, and then just simply find its way across the, we can say, top, and there may be some, we can say, disturbance at the backside also. So this is the basic engineering. In second case, let us suppose the wind is striking from this particular direction, that is theta is equal to 180 degree. That is theta is equal to 180 degree. In that case, if we want to draw the, we can say, wind, so in that case basically we can say that wind shall basically strike the backside of the solar panels, and some percentage that shall simply, we can say, blow away, and there may be some disturbance at this particular site, and when some wind energy shall some wind shall also flow from the bottom also. So that is the basic in judgment. Now in which case the wind forces are higher? When wind is flowing theta is equal to 0, when wind is flowing theta is equal to 180. In this case basically the solar panel orientation is helping us to, we can say, change the direction of wind and then just simply helping it to blow away. But in this case, if wind is flowing from this particular direction, the wind shall face the maximum resistance, because the wind shall get trapped here, and this shall be having the, we can say, maximum wind effects. So that is why the, as per the table we shall study shortly, that these coefficient for theta is equal to 180 are higher as compared to theta is equal to 0. The only problem is that regarding the higher, we can say, resistance to the wind in case wind is flowing from theta is equal to 180. So that is the, you can say, second concept that I want to discuss. Third concept is that why we are not talking about theta is equal to 90 degree. Because let us suppose this is the solar panel here. Let me just draw it in isometric. So when let us suppose when we are talking about this particular area, that is theta is equal to 90 degree. So in this case, only this we can say, only this shall be the resistance area. So this shall be very, very small as compared to, in the other case when we're talking about theta is equal to 0, this whole area was resisting the wind forces. So that is why we do not talk about theta is equal to, we can say 90 degree and 270 degree. We do not talk about these angles. We only talk about theta is equal to 0 and theta is equal to 180 degree. So I hope the concept is now clear to you. Now we can just simply, move on to the table. So in this table, we can see here that this whole solar panel, that is basically divided into different, we can say, areas. So first area is, we can say, A1, A2, A3 and B1, B2, B3. After that, C1, C2, C3 and D1, D2, D3. And if you're talking about theta is equal to 180, basically this whole A1, A2, A3 is, just simply shifted to the back side. And this D1, C1 and D1, that is basically shifted to the front side. Because in simple word, whatever, we are talking about the wind striking angle, that shall be resisted by A and B. And if we're talking about the secondary solar panels that are basically on its back side, we're talking about C1, C and D. So that is the, second, we can say, next concept that we do need to remember. Considering in our case, our first, the concept that we had learned was, the more the striking angle, the more the pitch, the more shall be the wind forces. Here also you can see that for 30 degree, the CPW is 1.5. For 15 degree, it is 1.2. And the second concept that we had understood was that for theta is equal to 180, when the coefficient shall be higher. In here, you can see that for 30 degree, it is 1.5. And here it is minus 1.6. Why, change in the direction? Because right now we are talking about the wind striking from the opposite direction. So obviously the effect of the wind from this side and effect from the wind from theta is equal to 1, that shall be exact opposite. So that is why, there is this change in the, we can say, change in the positive and negative of the pressure coefficient. So that is the next concept. After that, if we are talking about, we can say A1, A2, A3 and B1, B2, B3, theta is equal to 0. So CPW in our case shall be B and D. So if we are talking about the CPW, that is the windward sides, we are talking about the B, we are talking about the D. So B1, B2, B3, that shall be CPW, and D1, D2, D3 that shall be CPW. So in our case, if supposing our alpha is basically 20 degree, the coefficient that needs to be taken as 1.3, 1.2 and 1.5 and 0.75. So these are the, we can say, windward coefficient, and these are again the windward coefficients. So it is B1, B2, B3 and D1, D2, D3. So for these, ranges, for these range, we can just simply select the B and D. After that, if we are talking about the A and C, that is A1, A2, A3 and C1, C2, C3, that shall be leeward sides. So A1, A2, A3 and C1, C2, C3. So again, we can refer 0.8, 0.45 and 0.9 and 0.45. And here also you can see that basically when talking about the leeward sides, the coefficient are much less as compared to the windward, because wind shall be striking at this particular face first, and these faces, or we can say the lower half, is much more critical as compared to the upper half of the solar panels. So that is also finally, or assessed after a lot of research, and it is it can be said that when wind is striking from theta is equal to 0, the solar, we can say the lower panels of the solar array are much more critical. So that is why they are assigned as the windward sides. Upper arrays are lesser critical. So that is why they are assigned as the leeward sides. Similarly, when we're talking about theta is equal to 180 degree, all the parameters are reversed. That is, in here, CPW was assigned to the lower solar panels. When we're talking about theta is equal to 180, CPW is assigned to the upper solar panels. In here, you can see that these are the CPW. So in here, CPW was given to B and D. In here, theta is equal to 180, CPW is given to A and C. So all the parameters are reversed. After that, if you're talking about the CPL, the lower solar panels when wind is striking from the backside, that is assigned as the CPL. So when wind is striking from the backside, we can say that upper half of the solar panels are much more critical, and when wind is striking from this particular theta is equal to 0, the lower half is much more critical. So that is, the basic understanding of the basics of the wind engineering. And according to that, we can just simply find out the net pressure coefficient. So after that, if we're talking about the alpha equal to, we can say 20 degree. So in here also, we can calculate the CPW. So in here, minus 1.4, minus 1.45 for windward, and minus 1.4 and 1.4 for the C1, C2, C3. Again, for CPL, we can just simply calculate minus 0.75 and minus 0.9 and minus 0.7 and minus 0.7. So this is how, we can calculate the net pressure coefficient for the solar panels mounted on the ground. So according to that, we can just simply multiply that with the Ka and KL. And most of the times, we can just simply ignore the reduction in area to have some conservatives to be on some conservative side. KL, local net pressure factor, because there are no as such, we can say, cladding or sheeting, so that factor also can be taken as 1. So on the basis of that, we can just simply find out the Cshp, which when multiplied with the, we can say, corresponding wind pressure, can help us to calculate or help us to do the structural analysis and design of the solar panel structures, and similarly its foundations also. So whatever moment is coming from the, we can say, these solar panels, on the basis of that, we can design the foundations also. So this is the first picture, and we had already discussed this in great detail. This is the second picture. So in here, we can see that this is not a solar panel mounted on the ground. This is basically a car roof shed. So we can either refer to the monoslope free roof for this kind of analysis. We should not refer to the solar panels mounted on the ground for this particular case, because the height, the C value, that is very high. So in here also, this is there's this one more example of the, we can say, solar panels mounted on the ground. We can say the only difference in this picture and the top picture, the one that we had seen here, is basically there is this grouping that has been done, and some wind is allowed to pass. In here, you will see some gaps here. So that is also we can say this engineer is much more practical as compared to the engineer that has designed this lower solar panels. Why? Let me just share a practical aspect here. In here you can see some gaps that has been provided between the solar panels. So this grouping has been done, and this help us to ensure that some wind can get passed through these gaps also. It is not like that the whole this whole area has to resist the wind, and this grouping has been done, and on the basis of that, we can just simply find out. And one more thing that I liked in this picture is that he has tied this whole arrangement together. If you basically zoom in and see closely, he has provided various columns. He or she has provided various columns, and on the basis of that, he or she has tied this whole structure together. So it shall ensure that this whole array of the solar panel is, we can say, resisting the wind force together, and at the same time these small gaps ensure that wind shall simply pass and it shall not create any kind of disturbance. And it is also good that these gaps are aligned to one another. That is, the location of these gaps and these gaps and these gaps, they are all same, so wind can simply pass in the case of an extreme wind. But if you're talking about the lower picture, here we can see that the gap is provided at much more distance here. So this design shall be a little bit, we can say, heavy as compared to the upper one. But at the same time, the alpha I can predict that this alpha is not more than 15 to 20 degree. But in the upper picture, this alpha is higher, we can say the pitch of the inclination. So there is a small, we can say, substation also, which harvests this basically, or collect this electrical energy, and then basically transfer it to the final destination. So I think the picture is now clear to you on how you can calculate the net pressure coefficient for, we can say, the solar panels mounted on the ground.